Hello, Algebra students. We're ready for Chapter 6, Section 1, where we're going to be graphing systems of equations. We'll do this review together in class. I want everybody to put on their thinking cap because you already know how to graph an equation. So in this section, we're going to be graphing a system of equations. What does that mean? That means that there's going to be two equations in the same problem. All right, in this section, we're going to be solving by graphing. So you'll take the time to graph one line or one equation, and then you'll graph the second equation. So one at a time, you'll graph the two lines, and the solution is where they intersect. That's what you're going to be looking for. Do the two lines intersect? If they do intersect, they have a solution. We call these consistent. If they do not intersect, which would mean they were parallel lines, they're inconsistent. Inconsistent do not have a solution, which means they're parallel, so it's null set, no solution. They never intersect. All right, independent systems of equation are consistent system of equations. Consistent systems of equations. A consistent, in other words, one that has a solution is independent. Has one solution. Dependent systems of equations are also consistent. A consistent system, guess what? With unlimited solutions. Now what would that look like? We're going to talk about that. So if it's unlimited solutions, another word for unlimited is infinite. It'll have infinite solutions. Now if I were you, I'd probably have to stop and let all this soak in for just a second. Whoops, I erased system there. These are our vocabulary words. Now, working the problems, I assure you, you're going to find to be very easy. So it's the terminology that we're going to have to wrap our heads around. Consistent. Consistent systems of equations can either be independent or dependent. So both of these have solutions. So the one that is inconsistent is the one that does not have a solution. So that one stands alone. So within consistent equations, I don't mean to be saying inconsistent, I'm saying within consistent equations, you can have independent or dependent. Independent has exactly one solution, and dependent has infinite solutions. You can make the little infinity sign there. So a nice summary is provided at the bottom of this page. So let's look at this summary. A system of equations means there's two lines graphed in the same problem. So in this first example, there's exactly one solution. The two lines intersect right there, one solution. On the second picture, the two lines are one on top of the other. They're the same line. Oh, they're the same line, so they're dependent. They're the same line, so there's an infinite number of solutions. Infinite solutions. Both of these are consistent. For inconsistent, there's no solution. That means the two lines never intersect. If they never intersect, then they are parallel. There's no solution, so let's do null set. Zero solutions, no solution. Infinite solutions, one solution. So we have to graph our equations to find out which one of the three we have. Here we go. So on the next page, we start with some examples. All right, the first three, the graphs are provided for us. So we're supposed to determine using the equations and the graphs if they're consistent or inconsistent, and if it's independent or dependent, and then we have to also tell how many solutions they have. So notice that we have the same slope. Both lines have the slope of -1, so they're parallel lines, right? Parallel. which means there's no solution. So that's the last question. So no solution. The first question says, are they consistent or inconsistent? Well, the only one that is inconsistent are the ones that have no solution. So it's inconsistent. And if it's inconsistent, then it can't be dependent or independent because those are only under consistent. So we only have these two for the first problem. The second problem, we don't have the same slope. We actually have negative reciprocal slopes. So actually these are perpendicular, which doesn't really matter. What does matter is that they intersect at exactly one point. So that makes them consistent because there is a solution. There's only one solution, so that means it's independent. Independent with one solution. And those are the three questions we're supposed to answer. 1, 2, 3. Okay. In my third problem, they've graphed it for me. They're saying that they're the same line. If you don't believe them, I don't like to take their word for it. Let's take 8x minus 4y and turn that into slope-intercept form. We'll start by isolating our y. Subtract 8x from both sides. So negative 4y equals negative 8x minus 12. Divide everything by negative 4 to get y by itself. And when we do that, we end up with y equals positive 2x plus another positive 3. Oh, so it is the exact same equation as the one provided first. So they're the same line. So that means it's consistent because there is a solution. How many solutions? It has infinite solutions because they're the same line, and that makes it dependent. So those are our three questions we're supposed to answer. All right, let's move on down to the next example. All right, we're supposed to graph the system of equations. So graph each system, determine whether the system has no solutions, one solution, or infinite many solutions. And if the system has one equation, name it. So here we go. I'm going to do number 1. I'm going to leave you to do number 2. So I take my time and I come over to my graph and I find this, the y-intercept is 3. My slope is 2, so rise 2, run 1. There's 3 points. Take a straight edge. I'm going to use the piece of edge of my paper. And there's your first line. Then the second line, the y-intercept is at 3. Let's do a different color. So our y-intercept is at 3. Our slope is 1 over 2. So rise 1, run 2, or down 1, left 2. And get your straight edge. We already know that the two lines intersect at that y-intercept at the point 0, 3. So our solution, it says determine whether the system has a solution. It does. And it's 0, 3 is our solution. So it has one solution. One solution. I'm leaning on something I shouldn't lean on. Which means it's independent. I don't know why it's erasing. Okay, there it is. Independent and consistent. And I don't know why it's doing this. All right. One solution, independent, consistent. I'm going to leave the second one for you to try on your own. So you can pause here and do number 2. All right, now let's do number 3, where we need to get it in slope-intercept form. When I take my x over, it becomes a negative x. Now I need to divide everything by negative 1, so it becomes positive y, positive x, positive 2. So I come over and I know my y-intercept is at 2. I rise 1, run 1, and there's my points to draw my line. Whoops, I missed it pretty bad. That's okay. My next equation, I need to solve for y again. So I'll take my x to the other side. It becomes a positive x. And it's the exact same equation. So we already know that they're going to be the exact same line. So that means I have infinite solutions. Infinite solutions, which makes it consistent and dependent. Consistent and dependent. Remember, the only one that's dependent is the one that's the exact same line. So consistent, dependent. I'm going to leave number 4 for you to do on your own. So go ahead and pause and do 4. We'll check it together. All right, now we have to tackle word problems because life's going to come to us in situations where we have to set up our own system of equations. So Jake and Diego are riding their bicycles to get into shape. Jake rode 20 miles last week and plans to ride 35 miles per week. Diego rode 50 miles last week and he plans to ride 25 miles per week. Predict the week in which Jake and Diego will have ridden the same number of miles. So where do the two meet? Where do they intersect? So here we go. We'll start with Jake. And it said for him that he already went 20 and then he's going to try to ride 35 per week. So we'll let per week, each week be our X, and Y will be his total number of miles. And then for Diego, Y is still his total number of miles. And he has already traveled 50. There it is, 50 miles. My screen is blank. All right, and he is going to try to go 25 miles per week. So 25 per week. So here are our two equations. Okay, so I got interrupted. I'm not sure where we were. I think we wrote the two equations that we needed for Jake and Diego. And at the bottom of your page, that graph has already been provided for us. And so we see that they do intersect right about here. That would be at 3. When X is 3, they're going to intersect. I'm having a hard time. I'm predicting it's about 125. But here's what we can do. We'll say, well, when at 3 weeks, predict the week in which Jake and Diego will have ridden the same amount. I'm going to say at week number 3, or when X equals 3. So we can check ourselves by plugging 3. So if I plug in 3 for X into both equations and I do the math, they both end up giving me Y equals 125. So week number 3 is the correct answer. Okay? That's how you use a system of equations to solve a word problem. And I'm going to leave the second word problem for you to try on your own. But notice the graph has been provided for you and the point is highlighted. And see if you can figure out how many weeks it's going to take Alex and Amber to save the same amount of money. All right, thanks a lot and have a great day.